we are now ready to talk about the stress tensor. The stress tensor. So far, we have obtained the governing equations for a general flow, compressible, variable density, and we write this as d rho by dt plus div rho u equal to 0 for mass conservation. So that's continuity. And for momentum, d rho u by dt plus div u rho u equal to div tau minus grad p plus rho g. Okay, momentum equations. So this is one equation, these are three equations. Okay, so if we assume density is constant, and we don't have to, but for the sake of simplicity and because we will be dealing mostly with incompressible flows, so assume incompressible constant density flows. Assume rho is equal to a constant that is known. Then if we count the number of unknowns we have u, v, w, p, and plus the 9 components of the stress tensor. 9 components of tensor. And if we compare that, so that's 9 plus 4, that is 13 unknowns. And compare that to the number of equations, we only have 4 equations. So obviously, we cannot solve this system of equations. And even if you consider the assumption or the case for simple Newtonian fluids where the stress tensor is symmetric, in other words, tau xy equal tau yx, tau xz equal tau zx, and tau yz equal tau zy, and this is due to the fact of requiring equilibrium for a material point. So if we shrink this point, and we have x, y, so we have tau x over here, and tau xx, tau y, and tau y. And if we have for the stress components, we have over here tau xy, and over here tau yx, and over here tau xy, and over here tau yx. If you take the moments around this point caused by these forces, you can show that for this material to be stable and not spin to infinity, essentially we require that tau xy is equal to tau yx. And you can make the same argument for tau xz and tau yz. Okay, so if we make this assumption, then the stress tensor, for the stress tensor we only need 6 components. We only need 6 components of tau. So this leaves us with u, v, w, p plus 6 times tau. So we get 6 and 4, we get 10 unknowns. But we only have 4 equations. So what can we do over here? And this is the one of the main closure problems. We call this the closure problem for the momentum equations. Luckily, we can relate the stress to other variables, or if you think about it, if we ask the question, can we relate tau to u, v, and w? And the answer is yes, we can do that using continuum mechanics. So we're going to step back for a second right now and consider some basic mechanics for stress and strain. And in a basic mechanics setting, if you have some object or some rod of length L0, and you subject this rod to a force F, and at time this is t equals 0, after some time increment, then this thing gets extended by a distance delta L. So this whole thing is L0 plus delta L. And this displacement is called strain. Okay? Strain, we're going to call this epsilon. And, well, the normalized strain is epsilon. More specifically, that's delta L over L0. And we can relate so obviously the force and the strain are related, because the higher the force, the more displacement there will be. And depending on the material, the displacement may be different. You could have a very strong material that you can barely pull, or if you pull it, it may behave in a nonlinear fashion. But for basic solids, there is a linear relation, or basic materials, or the simplest of which, linear relation between F and delta L. And more specifically, if you normalize F by the area over here, so this has area A, then F over A is proportional to epsilon, or we can write sigma equal F over A, and that's equal to some coefficient E times delta L over L0. That gives you your very basic relation between stress and strain from a material that behaves linearly. We call this a linear material, basic linear elasticity theory. Okay, so now the question is, can we relate tau, we are after relating tau to u, v, and w. Okay, but we have to go through tau and epsilon. So the strain, strain specifically, we're going to be looking at strain rates. Okay, and then can we relate the strain? So we know that tau is related to epsilon. We know that tau is a function of strain rates. So this is strain rates, right? And then the question is, how can we relate the strain rates to u, v, and w? Well, they're obviously related for a fluid element, right? Because as the fluid element is stretched and rotated, that stretching and rotation is based on the velocity field itself. So let's find out what the strain is for a fluid element. We will now consider a small fluid element to illustrate the strain tensor, to derive the strain tensor. X, Y. I'm going to take a small fluid element of size delta x and size delta y. At this point over here, I'm going to have velocities u and v. At this point, we'll have u plus du by dx delta x, differential change, and v plus dv by dx delta x. Same thing over here. We will have u plus du by dy, the gradient of u in the y direction, delta y, and v plus dv by dy delta y. So at both of these points, the gradient, the velocity gradient, is going to move this point in the x direction and also in the y direction. du by dx and dv by dx, and so on. Same thing over here. Okay, so this is at time t equal 0. T equals 0. In a small increment, delta t, small increment time, what happens to this element? It's gonna obviously be stretched this point is going to go in this direction, that point that direction, and this guy in that direction. So we're going to have something that looks like this. Okay? And so if this is the origin O, this is still the origin O. Now what matters here are the distances. So this distance over here is the amount by which this point moved in the y direction, and that is dv by dx delta x times delta t. So this is dv by dx delta x times delta t, and this guy over here, this distance in the small amount of time, t equal delta t, this guy is du by dy delta y times delta t. Now this distance over here is the original distance delta x plus how much stretching happened in the x direction. So that's du by dx delta x, this guy, times delta t in a small increment of time. And same thing over here. This distance is the original delta y plus dv by dy delta y times delta t. Okay? Now, the strain for this element, obviously we have multiple strains in this two-dimensional case. We have the strain in this direction and the strain in the y direction, and also strains over here. So we're going to call this epsilon xx, epsilon yy, and these guys epsilon xy and epsilon yx. We follow the same nomenclature, epsilon iij, that's the rate of strain. So this is a rate per second on an I face in the j direction. Okay. The interpretation of epsilon xx, epsilon yy is really obvious. That's the displacement in the x and y directions. So epsilon xx is simply the rate of displacement in the x direction, and that's going to be this new distance minus the initial distance over the initial distance over delta t. So that's delta L over L0 over delta t. Now delta L is by how much this guy was stretched, and it was stretched just by this amount. Or you can take this total distance minus delta x. So that's delta x plus du by dx delta x delta t minus delta x over delta x times 1 over delta t, and delta x, delta x, delta x, delta x, delta t, and delta t, and you get this equal to du by dx. And similarly, epsilon yy is dv by dy. That's the rate of stretching in the y direction, and same thing for epsilon zz. We didn't illustrate that here. That's dw by dz. So really the normal strains are just related to the dilatation of the fluid element. Okay. Now something a little bit more interesting has to do with epsilon xy and epsilon yx. Well, first they're going to be equal just because of symmetry, and we define the epsilon xy and epsilon yx as the average rotation or stretching of this element. So if we take this angle here to be, I'm going to use blue, to be d alpha, and this angle over here to be d beta, then epsilon xy, epsilon yx are defined as the average of d alpha by dt, so rate of rotation, plus d beta by dt. So what is the alpha? What is the alpha and d beta? So all we have to do is focus on the rotation of these guys on the initial element. So tangent of d alpha is equal to simply this distance, dv by dx delta x delta t, over the side. In this case, we just need to measure the initial displacement. Higher order terms are not going to matter, so even if we carry this guy, it's not gonna make a big difference. And then this is going to be equal to dv by dx delta t. Now for small angles, small displacement, tangent d alpha is approximately equal to d alpha, and that's equal to dv by dx dt. So d alpha by dt is equal to dv by dx. And same thing, d beta will be approximately equal to du by dy dt, so that d beta by dt is equal to du by dy. And it's these two very important relations that will help us find the strain epsilon xy, so that epsilon xy equal epsilon yx, and that's equal 1 over 2 du by dy plus dv by dx. So that gives you the strain rate. The units of the strain, epsilon, is equal to meter per second times 1 over meters, and so that's equal to 1 over second. Okay, so a similar thing applies to all the other strains, so that epsilon xz is equal to epsilon zx, and that's equal to 1 over 2 dw by dx plus du by dz, and epsilon yz is equal to epsilon zy, and that's 1 over 2 dw by dy plus dv by dz. And when you put all these components together, you get the rate of strain tensor, and put it here in the matrix: epsilon xx, epsilon xy, epsilon xz, epsilon yx, epsilon yy, epsilon yz, epsilon zx, epsilon zy, epsilon zz. So now we related the strain tensor to the velocity field. So we had tau related to epsilon as f of epsilon, and now we related epsilon to the velocity field, f of u. So now we can relate tau as a function of the velocity field. So the relation between tau and the strain can get really complicated and is different for different types of fluids. So the stress strain relation for different fluids. So if you plot roughly the stress versus the strain, your most basic fluid, your most simplest material, is one that is going to react linearly, and that we call Newtonian fluid. Newtonian fluid. In this case, tau is equal to k epsilon. We'll see what this form is in a second, but I want to talk about other fluids as well, because there are many other different types of fluids we can deal with. So the idea here is there's just a basic linear relation between tau and epsilon. You apply this much tau, you're going to get this much strain. You double tau, then you're going to get this proportionality constant that is going to double the strain, and vice versa. Okay, but there are other types of fluids. Some of the more popular ones are fluids where they behave linearly initially, but then as you increase the stress, then they start the proportionality, the local proportionality constant, or the slope, the local slope, starts decreasing. Now remember, the local slope over here, this K, we know for basic fluids, we kind of already know that this is the slope over here is, so d tau by d epsilon is the viscosity. For these types of fluids, initially you're starting with a kind of constant viscosity if you want, but then locally the viscosity starts decreasing as you apply more stress. And we call these types of fluids shear thinning. Shear thinning fluids. And a classic example for shear thinning fluids, so shear thinning is paint, where you initially, once you take the your brush, you dip it in paint, and then you kind of push on the brush on the wall. That is gonna thin out the. It's going to reduce the viscosity essentially of the paint. It's going to thin it out. You're able to spread it. But then once you remove the stress, it's going to harden. And so that prevents dripping and all these bad things you don't want to have when you're doing paint. This is also called a pseudoplastic fluid. Another type of fluid has the opposite behavior of this, in that you have kind of this initial nice linear relation, but then you get this increase in the local viscosity. This is the opposite of these shear thinning fluids, and these are called shear thickening fluids. So shear thickening. A classic example of these types of fluids is cornstarch in water, where you put the cornstarch in water. If you kind of put some pressure on it, it's gonna harden, becomes a solid. If you remove the pressure, it starts flowing back again. So you remove the pressure, you're back here. You start behaving like a Newtonian fluid. If you increase the pressure, then it's going to harden up, becomes extremely resistant to forces, extremely resistant to motion. And also another example of shear thinning fluid is ketchup. Okay, now there are other types of fluids that initially behave like a solid. So take your toothpaste, for example, or mayonnaise, where you have this kind of initial barrier where you have to apply an initial stress called a yield stress. And then you have some interesting behavior, and this is called a plastic fluid. This is plastic fluid. And an idealization of the plastic fluid is to take this just as a linear relation, and this is called an ideal Bingham fluid, ideal plastic. Ideal plastic. You have mayo, toothpaste, mud flows, slurries, etc. Okay, kind of this gives you a general idea of the complexity of the relation between tau and epsilon. And in general, there's this huge matrix of different multipliers relating tau and epsilon. One simple generic model is to say tau ij is equal to some constant epsilon ij to the power n. And when n is less than 1, we get pseudoplastic, so shear thinning, pseudoplastic. N equal 1, you get Newtonian, and then n greater than 1, you get shear thickening fluids, shear thickening fluids. Okay. All of these are options, but there's also other complications with non-Newtonian fluids where you have the history of the stress on the fluid plays a role, time history of the stress on the fluid plays a role. But in this course right now, we're going to be primarily dealing with Newtonian fluids. So let's get back to that. For Newtonian fluids, from linear elasticity and some observations for the relation between tau and epsilon, there is a general form that I'm just going to spit out for the stress tensor that relates the stress tensor to epsilon and then directly to the velocity field, and that is given by the standard Newtonian stress tensor. Tau ij is equal to mu dui by dxj plus duj by dxi plus delta ij lambda div u. This mu is the proportionality constant, or called viscosity, and it's a proportionality constant between the stress and the strain in this case. Proportionality constant, sigma equals mu epsilon, and this lambda is called the second coefficient of viscosity. And more on that in a little bit. For incompressible fluids, this guy will be 0, so we don't even care what lambda means. But for flows where you have really significant dilatation, you have to take this into account. Stokes made the assumption that lambda equal minus 2 over 3 mu. We'll see how and why he made this assumption. But primarily, this is a relation for a Newtonian fluid between the stress and the velocity. And you can simply obtain the components directly by plugging some numbers in. And also, this is the Kronecker delta. Delta ij is equal to 1 if I equals to j and 0 otherwise. So only the normal stresses are affected by this dilatational component. And you could say tau xx is equal mu du by dx plus du by dx. So you have 2 mu du by dx plus delta 1 which is 1 plus lambda div u, and tau xy is equal to mu du by dy plus dv by dx, and tau xz is equal to mu du by dz plus dw by dx. Same thing, tau yx is equal to mu dv by dx plus du by dy, and notice how these are equal. And tau y is 2 mu dv by dy plus lambda div u, and tau yz equal to mu dv by dz plus dw by dy, and tau zx is equal mu dw by dx plus du by dz, So notice how tau zx is equal to tau xz, and tau zy is equal to mu dw by dy plus dv by dz, and tau zz is equal to 2 mu dw by dz plus lambda div u. That gives you the full stress tensor. Okay. Now the units of the stress tensor, the units of the stress are obviously, so the units of tau are newtons per meter squared. Okay, and the units of, so that will allow us to obtain the units for mu. So mu, the units of mu are the units of tau over the units of epsilon, the rate of strain, and that's Newton per meter squared, and this is 1 over second. So times 1 over second, you get a second here, Newton dot seconds per meter squared. So now the final note on the second coefficient of viscosity. Another form of the stress tensor is to lump the pressure into the stress tensor itself and say that sigma is equal to minus p delta ij. So we're only adding, because the pressure force is normal, it only contributes to the normal components of the stress tensor. So we're only adding that to the tau xx, tau yy, and tau zz, plus mu dui by dxj plus duj by dxi, okay, plus lambda delta ij div u. Okay, now this general formula, Stokes went ahead and said, well, the pressure, I'm going to define the mechanical pressure as equal to the average of sigma xx, sigma yy, and sigma zz, and that average pressure should be equal to P. Okay, that's his argument. Now, if you take this formula and plug it in here, you get minus 1 over 3, so sigma xx, so you have 3p, you have minus 3p over 3, that gives you p, but you also get plus lambda plus 2 over 3 mu, remember, because you have the 2 mu du by dx and du by dv by dy plus dw by dz, div u is equal to p, and so this implies that lambda plus 2 over 3 mu div u must be equal to 0. And obviously div u is not necessarily 0 in general, so this led him to the assumption that lambda plus 2 over 3 mu is equal to 0, so this implies that lambda equals minus 2 over 3 mu. And, you know, that just takes the problem away, but it's still a good working model. And so the most general form of the stress tensor, whether you include the pressure or not, let's just include the pressure. Sigma is minus p delta ij plus mu dui by dxj, so that's sigma ij, plus duj by dxi minus 2 over 3 mu div u. That's the most general form of the full stress tensor. This includes the pressure, so obviously when you put this form into the governing equations, you should remove the pressure gradient or simply use tau, right? So choose this thing as tau ij if you're explicitly including the pressure into your governing equations.